In this video, I am going to talk about the distributed operating systems. The following topics are covered: introduction to distributed systems, goals of distributed system, hardware concepts, bus-based multiprocess, switched multiprocess, bus-based multi-computers, and switched computers. Operating systems. An operating system is an interface between a computer user and computer hardware. An operating system is a software which performs all the basic functions like file management function, memory management function, process management function, handling the input and output, and controlling peripheral devices such as disk drives and printers. Definition of a distributed system. A distributed system is a collection of independent computers that appears to users as a single coherent system or a single computer. And this is a diagram of a distributed system. A distributed system organized as a middleware. The middleware layer extends over multiple machines and offers each application uh, the same interface. Goals of the distributed system: making the resources accessible to all the users connected to the distributed system and exhibit the distribution transparency, supporting the openness and scalable in terms of size and in terms of geographical location also. It supports different types of transparency in a distributed system. The first one, access transparency, which hides the differences in data representation and how your resources is accessed by different users. Location transparency, this is going to hide where your resource is actually located. Migration transparency, this is going to hide that your resource may move to another location. Relocation transparency, this is going to hide that your resource may be moved to another location while then used by other users. Replication transparency, this is going to hide that your resources is replicated. Concurrency transparency, this is going to hide that a resource will be shared by several competitive users. And last one is a failure transparency. This is going to hide the failure and recovery of a resource. Advantages of a distributed system. First one, economics, speed, inherent distribution, reliability, and incremental. The real driving force behind the trend towards decentralization is economics. With microprocessor technology, for a few $100, we can get a CPU chip that can execute more instructions per second than one of the largest 1980s mainframes. If you are willing to pay twice as much, you can get the same CPU but running at a somewhat higher clock speed. As a result, the most cost-effective solution is frequently to harness a large number of cheap central processing units together in a system. Thus, the leading reason for the trend toward distributed system is that these systems potentially have a much better price and performance ratio than a single large centralized system. A slight variation on this scheme is the observation that a collection of microprocessors cannot only give a better performance ratio than a single mainframe, but may give an absolute performance that no mainframe can achieve at any price. Some authors make a distinction between distributed systems, which are designed to allow many users to work together, and parallel systems, whose only goal is to achieve maximum speed up on a single problem, as our 5 lakh million instructions um, per second machine may have. So we believe that this distinction is difficult to maintain because the design spectrum is really a continuous. We prefer to use the term distributed system is the broadest sense to denote any system which multiple interconnected central processing units work together. The next reason for building a distributed system is that some applications are inherently distributed. A supermarket chain may have many stores, each of which gets goods delivered to locally, makes local sale, and makes local decisions about which vegetables are so old or rotten that they must be thrown out. It therefore makes sense to keep track of inventory at each store on a local computer rather than centrally at the corporate headquarters. After all, most queries and updates will be done locally. Nevertheless, uh, from time to time, top management may want to find out how many rota baggage it currently owns. One way to accomplish this goal is to make the complete system look like a single computer to the application program, but implement decentrally with one computer per store as we are describing it. Another inherently distributed system is what is often called a computer supported cooperative network, in which a group of people located far from each other are working together. Another potential advantage of a distributed system over a centralized system is higher reliability. Finally, the incremental growth is also potentially a big plus point. Often a company will buy a mainframe with an intention of doing all its work on it. If the company proposes, uh, sorry, prospers and the workload grows, at a certain point, the mainframe will no longer be adequate. The only solutions are either to replace the mainframe with a larger one. Both of these can wreak major havoc on the company's operation. In contrast, with a distributed system, it may be possible simply to add more process to the system, thus allowing it to expand gradually as the need arises. So these are the advantages summarized on the screen. Some of the advantages of distributed system over isolated personal computers. Given that microprocessors are a cost-effective way to do business, why not just give everyone his own personal computer, let people work independently? For one thing, many users need to share the data. For example, airline reservation clerks need access to the master database of flights and existing reservations. Giving each clerk his own private copy of the entire database would not work, since nobody would know which seats the other clerks had already sold. Shared data are absolutely essential to this and many other applications. So the machine must be interconnected. Interconnecting the machines lead to distributed system. Sharing often involves more than just data. Expensive peripherals such as color laser printers, prototype setters, and massive actual storage devices are also the needed for this distributed system. Another reason to connect a group of isolated computers into a distributed system is to achieve enhanced person-to-person communication. Finally, a distributed system is potentially more flexible than giving each user an isolated personal computer. Although one model is to give each person a personal computer and connect them all with the local area network. Although distributed systems have their strength, they also have their weaknesses. In this section, we will point out few of them. We have already hinted at the worst problem, software. With the current state of the art, we do not have much experience in designing, implementing, and using distributed software. What kinds of operating systems, programming languages, and applications are appropriate for the system? How much should the user should know about the distribution? How much should the system do, and how much should the users do? The experts differ. They are, as more research is done, this problem will diminish, but for the moment it should not be underestimated. Second potential problem is due to the communication network. It can be lost messages, which requires special software to be able to recover, and it can become overloaded. Finally, the easy sharing of data, which we described above as an advantage, may turn out to be a two-edged sword. If people can conveniently access data all over the system, they may equally be able to conveniently access data that they have no business with. In other words, security is also often a problem. For data that must be kept secret at all the costs, it is often preferable to have a dedicated, isolated personal computer that has no network connection to any other machine and is kept in a locked room with a secure safe in which all the software is possible. The disadvantages of the distributed systems are summarized here. The first one is the software, second one is networking, third one is the security. Even though all the distributed system consists of multiple central processing units, there are several different ways the hardware can be organized, especially in terms of how they are interconnected, how they are used. Various classification schemes for multiple central processing units computer systems have been proposed over the years, but none of them have really caught on and been widely adopted. Probably the most frequently cited taxonomy is Flint's taxonomy, which was introduced in 1972. A computer with a single instruction stream and a single data stream is called SISD. All traditional uniprocessor computers fall in this category, while the personal computers in large dimensions. The next category is SIMD. Single instruction stream, multiple data stream. This type refers to array process with one instruction unit and that fetches an instruction and then commands many data units to carry it out in process, each with its own data. These machines are useful for computation that repeat the same calculation on many sets of data. For example, adding up all the elements of 64 independent vectors from supercomputers or SIMD. The next category is MISD, multiple instruction stream, single data stream. No known computer fit in this model. Finally, MIMD, which essentially means a group of independent computers, each with its own program counter, program, and data. All distributed systems are MIMD, so this classification system is tremendously useful for our purpose. We divide all MIMD computers into two groups, those that have shared memory, usually called multiprocessor, and those that do not, sometimes called multi-computer. The essential difference is that in a multiprocessor, this is a single virtual address space that is shared by all the central processing units. If any CPU writes, for example, the value 44 to address 1000, any other CPU subsequently reading from its address 1000 will get the value 44. All the machines share the same memory. In contrast, in a multi-computer, every machine has its own private memory. If one CPU writes the value 44 to address 1000, when another CPU reads address 1000, it will get whatever value was there before. The write of 44 does not affect its memory at all. A common example of a multi-computer is a collection of personal computers connected by a network. Each of these categories can be further divided based on the architecture of the interconnection network. In the diagram shown on the screen, you can describe these two categories as a bus and switch. By bus, we mean that there is a single network, backplane, and bus, cable, or other medium that connects all the machines. Cable television uses a scheme like this. The cable company runs a wire down the street, and all the subscribers have tapes running to it from their television set. Switched systems do not have a single backbone like cable television. Instead, there are individual wires from machine to machine. With many different writing patterns in use, messages move along the wire with an explicit switching decision made at each step to route the message along one of the outgoing wires. The worldwide public telephone system organized in this way. Another dimension toward taxonomy is that some systems, the machines are tightly coupled, and in others they are loosely coupled. In a tightly coupled system, the delay experienced when a message is sent from one computer to another is short, and the data rate is high. That is, the number of bits per second that can be transferred is large. In a loosely coupled system, the opposite is true. The inter-machine message delay is large and the data rate is low. For example, two central processing unit chips on the same printed circuit board and connected by wires etched onto the board are likely to be tightly coupled, whereas two computers connected by a 2400 bits per second modem over the telephone system are certain to be loosely coupled. Classification. General classification. Multi-processor, a single address space among the processor. Multi-computer, each machine has its own private memory. Operating system can be developed for either type of environment. Bus-based multiprocessor consists of some number of CPUs all connected to a common bus, along with a memory module. A simple configuration is to have a high-speed backplane or motherboard into which CPU and memory cards can be inserted. A typical bus has 32 or 64 address lines, 32 or 64 data lines, and perhaps 32 or more control lines, all of which operate in parallel. To read a word of memory, a CPU puts the address of the word it wants on the bus address line, then puts a signal on the appropriate control lines to indicate that it wants to read. The memory responds by putting the value on the of the word on the data lines to allow the requesting CPU to read in it. So write works in a similar way. Tightly versus loosely coupled. Tightly mean delay experience when a message is sent from one computer to another is short and data rate is high. Mostly used as parallel system. Example, two central processing unit chips on the same printed circuit board connected by wires. Loosely mean opposite to the previous case, inter-machine messages delay is large and data rate is low. Mostly used as distributed system. Example, two computers connected by 2400 bits per second modem over the telephone system. Bus-based multiprocessor. Bus-based multiprocessor has multiple central processing units all connected via a common bus. A bus has 32 or 64-bit address line, 32 or 64-bit data line, and 32 or more bit control line. Memory management is coherent. To improve the performance, cache memory is used. Cache memory management, write-through cache or Snoopy cache. In bus-based multiprocessor, many researchers have studied this same problem. Suppose if the cache memories are designed so that whenever a word is returned to the cache, it is returned through a memory as well. Such a cache is not surprisingly called a write-through cache. In this design, cache hit for read do not cause bus traffic, but cache misses for reach and all writes and hits and misses cause bus traffic. In addition, all caches constantly monitor the bus. Whenever a cache is a write occurring to a memory address present in its cache, it either remove that entry from its cache or update the cache entry with a new value. Such a cache is called Snoopy cache or sometimes called a snooping cache. In, in bus-based multiprocessor, uniform memory access. Caching is vital for reasonable performance. Example, caches on a shared memory multiprocessor. It wants to maintain a cache coherency. One is a write-through cache. Any changes to cache are written through the memory only. Snoopy cache, any changes to cache are either removed or updated with a new value. A design consisting of Snoopy write-through caches is coherent and invisible to the programmer. To build a microprocessor with more than 64 processors, a different method is needed to connect the central processing units with the memory. One possibility is to divide the memory up into modules and connect them to the CPUs with a crossbar switch as shown in the diagram. Each CPU and each memory has a connection coming out of it as shown in the diagram. At every intersection is a tiny electronic crosspoint switch that can be opened and closed in hardware. When a CPU wants to access a particular memory, a crosspoint switch connecting them is closed momentarily to allow the access to take place. The virtue of the crossbar switch is that many central processing units can be accessing the memory at the same time. Although if two central processing units try to access the same memory simultaneously, one of them will have to wait. The downside of the crossbar switch is that n central processing unit and n memory. N square crosspoint switches are needed. For large n, this number can be a prohibitive. As a result, people have looked for and found alternative switching network that require fewer switches. The Omega network that is shown on the screen on right hand side, the B diagram. This network contains four 2 by 2 switches, each having two inputs and two outputs. Each switch can route either into input to either output. A careful look at the figure will show that with the proper settings of the switches, every CPU can access every memory. These switches can be set in nanoseconds or parallel. The crossbar switch, it is useful to connect multiple central processing units with many memory modules. Crosspoint switch is used to connect central processing unit with memory module based on requirement. To connect n CPUs and n memory module, n square crosspoint switches are required. For larger n, the interconnection is complex. Omega switching network, it contains four 2 by 2 switches having two input and two output ports, switching between them. Less complex compared to crossbar switch, as is Omega switching requires only n by 2 switches to connect n CPUs with n memory module and log to n switching stages. Limitations. For larger values of n, the switching time is larger and increases delay in instruction execution. Moreover, it is expensive. Switched multiprocessor delay and cost, non-uniform memory access, it attempts to reduce the delay in case more cost. Attempts to reduce cost gave rise to a hierarchy where CPUs have their own memory and access cost to memory is non-uniform. Conclusion about multiprocess. Building a large, tightly coupled shared memory multiprocessor is possible, but it is difficult and expensive.